Hello, I'm going to work through the solutions of the 2025 Scholarship Calculus Examination 93202. We've already looked at questions 1, 2 and 3. I've posted videos about those, so we're going to start with question 4 today. Well, when I say today, I mean in this video. So here we have it. We are asked to evaluate the definite integral from 0 to 1 of the inverse sine of x. So the inverse sine function is shown in the graph above. The question effectively is asking us to calculate this pink area. I think it turns out easier to calculate this rectangular area and then to subtract off this purple area. The rectangular area, its base is 1, its height is pi over 2, so it's 1 times pi over 2. Excuse the bad colour, I'm not going to use it very much. And the purple area, which we're subtracting off, is going to be an integral. If we treat y as our variable, it's an integral from 0 to pi over 2 along the y-axis of the height of this curve, and this curve is the inverse of the inverse sine function, is just the sine function, sine y dy, and that will give us an answer. I'll persist with yellow for another line or two at least. Integrate sine y, you get negative cosine y, and that's evaluated at pi over 2 and at 0. So this is equal to pi over 2, and then take off cosine of pi over 2. Now this is pi over 2 here. Cosine of pi over 2 is 0, so it's minus 0, and then take away minus 1. So, getting rid of the yellow and the purple, we get an answer of pi over 2 minus minus, that's going to be minus 1. And that will give us the answer to that question. You can write out a value for that. Pi is 3.14. So this is 1.57. Take off 1, so we get 0.57 or something similar to that. If x equals sine y, that's just another way of writing y equals inverse sine of x. Show that dy by dx has this derivative. To do this question, it's just implicit differentiation on this equation. Y is our dependent variable, x is our independent variable. So we differentiate x, you get 1. You differentiate sine, you get cosine. And because this is a function of y, we have to use the chain rule and multiply that by dy by dx. Therefore, dy by dx is 1 divided by the cosine of y. And cosine of y, using the identity sine squared y plus cosine squared y equals 1, we can rewrite that as cosine squared y is 1 minus sine squared y, and we can therefore write cos y is the square root of 1 minus sine squared y. And sine squared y, and the question tells us that sine y is equal to x. So this is the same as 1 over the square root of 1 minus x squared, as required. Hence, or otherwise, find the minimum value of sine inverse of 2x plus sine inverse pi over 4 minus 2x. To find a minimum, we differentiate. Differentiate sine inverse, we get this thing here, but we've got an argument of 2x, so we need to replace the x by 2x. So you get 1 over the square root of 1 minus 2x squared, and then you have to multiply by, using the chain rule, the derivative of what's inside, so that's 2, and then plus, same thing over here, 1 over the square root of 1 minus, now it's pi over 4 minus 2x squared, then differentiate what's inside, that's going to be multiplied by minus 2. And to find a minimum, we need to set this to 0. The question says you can assume that the answer gets the minimum, so we don't have to check that it's minimum or maximum, or maybe a point of inflection. A way to solve this from here is if we just multiply through by both of these square roots. And multiply through by 1 minus pi over 4 minus 2x squared. Multiply through by both of those. One of these terms is going to cancel over here. One of them is going to cancel here. And we will get, so therefore, this one will become the square root of 1 minus pi over 4 minus 2x all squared. This has got a minus sign. Let's shift it on to the other side as well. So this one, that multiplying by this is going to cancel. Multiplying by this will give us a contribution. So 1 minus 2x squared. Actually, both of these are going to have a 2 outside. We can cancel that too. Two square roots are the same, only if the arguments inside are the same. Let's multiply this out. Pi over 4 squared minus pi over 2 times x. There's two of them. Minus pi times x. It's got a minus sign out here. It's going to be plus, and then plus 4x squared with a minus sign, and that's going to be equal to 1 minus 4x squared. The minus 4x squareds are the same. The ones are the same. Shift this on the other side. That's going to say pi x has got to be pi over 4 squared. And finally, x is going to be divided by pi, so we have 1 pi on the top over 16. The question says find the minimum value, so we have to then substitute that back in. So g of pi over 16 is sine inverse pi over 8, 2 pi over 16. Well, let's write it. It is 2 times pi over 16, and then plus sine inverse pi over 4 minus 2 pi over 16. This is pi over 8. And this is a quarter minus an eighth, which is going to be an eighth as well. So we've actually got two of those, and you can work that out. And I've done that, and I found 0.807. It's a little bit funny because this pi is sort of artificial in here. It's telling us Not that the angle was pi. We're familiar with seeing things like sine pi over 4, but sine inverse pi over 4 says what is the angle whose sine is pi over 4. So normally angles along this axis on a sine graph, but it's telling us we've got a value pi over 4 up here somewhere, and we're trying to find out what the angle is, or pi over 8 or 16. So it's a little bit funny to put pi's inside an inverse sine function. I mean, they're valid as long as the value inside here is between -1 and 1, but you couldn't put 2 pi in here. Sine inverse 2 pi. There's no angle whose sine is 2 pi, because sine always falls between 0 and 1, and 2 pi is 6.28 or something. So that's that question. Part B, consider the function f of x equals 1 over r to the power of r, all of that to the power of 1 over r plus 1, times x to the power of r, where r is a positive real constant, so and x is bigger than 0, find the value of r for which the function is a solution of the differential equation. The derivative of f is equal to the inverse function of f. And then it tells us a little bit more about inverse functions, that an inverse function is a function that when you apply that function to the inverse function, you get back to the x value for all x in the domain. So yeah. A way to find the inverse function is just, if you write the equation as y equal 1 over r to the power of r, 1 over 1 plus r times x to the power of r. A way to write this is just to try and rearrange this equation to get x as the subject, and then what you're left with will be the inverse function. I think it's a good idea to rewrite this equation as just k x to the power of r. It tells us r is a positive real constant, so all of this mess here is just going to be some other constant, k equal to whatever the mess is. You can write it out if you want. All of this is k. It's going to make our algebra look easier. So if you want to rearrange this to get x, so if we divide by k, we get x to the r, and then if we raise that to the power of 1 over r, we get x. So this function here is our inverse function. So f inverse of x is going to be this thing here, but with the y replaced by an x. So now we have got an equation for the derivative has to equal this. So the derivative of this is just k, a constant, and this is just x to the power of r. It's a very, very simple differentiation. You put the r out the front. We've got a k, and then x to the power of r minus 1. And that has to equal x over k to the power of 1 over r. That's what we're trying to solve. So this is the derivative, and this is the inverse function. The first thing that's going to be apparent is that these x terms have to have the same power. Otherwise, they can't possibly be true for all values, all powers. So we need r minus 1 to be equal to 1 over r. And this is just a quadratic. Multiply through by r, you get r squared minus r, and then minus 1 equal to 0. It's actually a very famous quadratic. It's the quadratic that gives the golden ratio. So I can see straight away that r is going to be equal to phi. There's actually two solutions to a quadratic, but one of them won't be positive. So we've got a product of roots that's negative, so only one of them is going to be positive. So, and we're told that r is a positive real constant. So you can use the quadratic formula if you want. So r is equal to minus this, so it's 1 plus or minus the square root. B squared is also 1 minus 4ac. It's another one that's divided by 2a. So it's 1 plus or minus root 5 over 2. And we have to have 1 plus root 5 over 2, which is the golden ratio. Technically, that's all the question asks us to do, to find that value of r. And we can check the constant. So we've got r times k is equal to 1 over k to the power of 1 over r. If we take the left-hand side, that's r times r to the power of r. We've got 1 over r to the power of r to the power of 1 over 1 plus r. If we raise that to the power, raise both sides to the power of r, let's write it as 1 over k, power of 1 over r. Raise both sides to the power of r, then we'd get r to the power of r, 1 over r to the power of r, to the power of r over 1 plus r, has to equal 1 over k. This is a power of 1. This is a power of, so this is going to get a minus 1 when we put it in there. So it's 1 over r to the power of r over 1 plus r to the power of minus 1. And this is 1 over r to the r over 1 plus r minus 1 plus r over 1 plus r minus r, they cancel. So you get left with minus 1 over this, so that's 1 over r to the power of r to the power of minus 1 over 1 plus r. And that minus is just saying we've got this thing flipped upside down, so that's 1 over k as required. Probably should not write those in down here and just put equal signs. So we take the left-hand side. We take the left-hand side, so raise both to a power of r. And then work with the left-hand side. The left-hand side raised to the power of r is going to be this. And we do the algebra and you see this is 1 over what we defined as k. And so this is true for all r. And as I said, the only real working you needed to do was identify that you've got the same power of r here. And you get the you get the golden ratio as our value of r. Okay, part C. The graph below shows part of the graph of h of x equal to sine of the exponential of x. Find the value of the limit as h goes to negative infinity and h goes to infinity of h of x, or state clearly if they do not exist. Well, to start with, let's just do the limit as h goes to negative infinity. So the limit as h goes to negative infinity, I'll put a positive. Of sine of e to the x. We can calculate that by taking the sine of the limit as I've written h, as x goes to negative infinity. Read one thing, something else goes into your head, and you write the wrong thing on the bit of paper or screen, e to the power of x. And it's fine to do this because the limit as x goes to negative infinity of e to the x is 0. So this is basically the sine of 0, which is 0. So that's the first one done. The other one, perhaps more interesting, so we can see this oscillating behavior that comes from the periodic behavior of the sine function. But this exponential inside means that when we continue this is going to go up and down more and more frequently until it's basically going up and down on top of itself. Maybe we don't want to mess on our page, but that's what it's going to look like. And so you can probably reason just heuristically or waving your hands that this is going to go up and down so frequently that it can't possibly have a limit. One way that I have looked at that is to look at the period of sine e to the power of x. Now, it's not going to be a constant period. It's going to vary as we go out. So in the period, we've got an x value. We want e to the power of x, say, equal to 2n pi for some large value of n. And then we want to investigate also e to the power of x equal to 2n plus 1 pi. And the difference in x values here will tell us how big or how small that period is getting. So e to the power of x is some multiple of 2 pi, and then it's the next multiple of 2 pi. So if we subtract these two things, so the period's going to be the difference between the two x values. So let's call this one x1 and this one x2. So if we subtract those, we want x2 minus x1 basically. So we haven't got those yet. We've got these exponential things. If we take the logarithms of e to the x1, that will give us x1, which will be the logarithm of 2n pi. And we take the logarithm of e to the x2, that will give us x2, which will be the logarithm of 2n plus 1 pi. And if we subtract these two things, x2 take off x1 is the logarithm of 2n plus 1 pi take off the logarithm of 2n pi. That's the logarithm of 2 plus the logarithm of n plus 1 plus the logarithm of pi. Take off the logarithm of 2, take off the logarithm of n, and take off the logarithm of pi. All of these cancel, so we're just left with a logarithm of n plus 1, take off the logarithm of n, which is equal to the logarithm of n plus 1 over n, which is equal to the logarithm of 1 plus 1 over n. And we're looking at this as n goes to infinity, because we want to go a long way out. That's e to the x. X goes to infinity. N, we're going to get many things out here. 1 over n becomes 0. Logarithm of 1, which is 0. Logarithm of 1 is 0. So this means our period is going to 0. It means we're going up and down as rapidly as you could imagine. And so there is no limit. At one instance, we're up at 1. Next instance, we're down at -1. And this is just happening so rapidly. Then part 2 says find the exact value of A that generates the maximum value. So yeah, let's write up here first. The limit as x goes to -infinity of h of x equals 0, and the limit as x goes to infinity of h of x does not exist. Rapid oscillations. Between h of x equal to 1 and h of x equal to -1. Find the exact value of A that generates the maximum value of the definite integral. So if we've got an integral equal to we want to maximize this. To find maximums, we find derivatives. Derivatives of integrals are opposites, so we just get rid of the integral basically. So and we're differentiating with respect to A as our variable, the maximum value of A. So that's our variable. So we can go di dA, and what you get is you get the sine of E evaluated at A plus 1, and then take off the sine of E evaluated at A. And we want to set that to 0. Now, the arguments can't be the same. E to the A plus 1 is never going to be equal to E to the A, because exponential is monotonously increasing. It's always increasing. So if we go out one more, we're always going to get a different value. But the sine function is periodic. So when we've gone out different amounts, we can get to the same value. And this repeats many times. But because of, so the value that we want here is we want a value of A, and then we want the other value to be pi minus A. So we want E to the A plus 1 to be equal to pi minus E to the power of A. So we've got this value here is E to the power of A, and this value here is pi minus E to the power of A. And when you've got those there, we get the same function value. when we take the sine of these two things. So we've got this expression here. We can write, I think, the exponential terms on one side. We can factor here e to the a times e for plus 1 equal to pi. We can divide, so we get e to the a is pi divided by e plus 1. And to get a, we can take a logarithm. A equals the logarithm pi over e to plus 1. And you can work that out. Negative 0.169. Say the right thing, write the wrong thing down. And that's us done. Any questions, put them in the comments as usual. And I'll see you next time with a different examination, because we've finished Scholarship 2025 Calculus examination. Farewell.